Welcome to The Explainer. Today, we're diving into a huge breakthrough from Google. And here's the kicker. It's not about a bigger, faster chip. It's about a smarter idea. So let's kick things off with a question that honestly sounded like pure science fiction just a little while ago. You see, the biggest thing holding AI back right now, it isn't actually processing power. Nope, it's memory. And it turns out the solution might not be more silicon, but just better math. And this right here, this is the number that just sent massive shockwaves through the entire tech world. Back in March, Google dropped an announcement about a new technology that could slash the memory needed for a really critical part of AI by a factor of 6. Okay, so to really get why this is such a game changer, we've got to talk about AI's biggest weakness. It's just got this insatiable, ravenous appetite for memory. And it's a problem that gets worse, literally, with every single word you type into a chat window. You know, the thing that's eating up all the memory isn't the AI's core brain, what we call its weights. Now, the real culprit is its short-term memory, its working memory. It's called the KV cache. And really, the best way to think about it is like a temporary notebook the AI scribbles in to keep track of what you've been talking about.
And this is such a critical difference. The AI model's main programming, its weights, that's a fixed cost. It's a one-and-done deal. But the KV cache? Oh, that just grows and grows and grows with every word, every token. And that's what creates what engineers grimly call the memory wall.
I mean, the scale of this problem is just staggering. Get this, for a big 70 billion parameter model that's only serving 512 users, the KV cache alone can swell up to 512 gigabytes. That's almost 4 times more memory than the entire AI model needs just to exist.
So, you're probably thinking, okay, why not just compress the data, right? It seems obvious. Well, in the computer world, compressing data, or quantization, is kind of like rounding numbers. So instead of storing, 3.14159, you just store 3.1. It saves a ton of space, but you lose some precision. And all the old ways of doing this for the KV cache were, frankly, pretty broken.
Yeah, these old methods had this hidden tax, this hidden cost. To get the original numbers back correctly, you had to store this extra bit of data, metadata, right alongside them. It was like packing an instruction manual with every single number. This added 1 or 2 extra bits for every value, which totally ate up all the savings. It basically defeated the whole purpose of compressing in the first place.
And this is where Google's TurboQuant just completely changes the game. It uses this 2-stage process that's not just effective, it's elegant. It gets rid of that whole metadata problem using nothing but clever math.
So it's basically a 2-step assembly line that works in real time. First, you've got this technique called PolarQuant that does the heavy lifting, squeezing the data down. Then, right after, a second process called QJL swoops in to clean up, checking for any little mistakes and fixing them perfectly.
All right, let's get into the weeds a bit here, because this is cool. The genius of PolarQuant is that it switches how it describes data. It goes from standard Cartesian coordinates to polar coordinates. Okay, think of it this way. Instead of saying go 3 blocks east, then 4 blocks north, which is 2 instructions, you just say, go 5 blocks in that direction. It's one clean, super efficient instruction to get to the exact same spot.
Now here's the really mind-bending part. The secret sauce is something they call a random rotation. I know, it sounds totally backward, right? But by spinning the data around in this high-dimensional space, its structure becomes, well, predictable. So predictable that all that junk metadata we talked about, it just vanishes. You don't need the instruction manual anymore. Okay, so on to step 2, QJL. The easiest way to think of this is as a perfect mathematical proofreader. It looks at any tiny leftover errors from the compression stage, and using just a single bit, literally a +1 or a -1, it calculates a perfect correction. This makes sure the AI's final answer is totally unbiased and accurate. It's amazing.
Okay, so all this clever math is great, but what does it actually do? What are the real-world results? Well, let me tell you, the numbers are pretty mind-blowing. First up, a 6-fold reduction in that KV cache memory. TurboQuant can squeeze data all the way down to just 3.5 bits per value. That is a massive, massive leap in efficiency.
And it's not just about saving space. It's about speed. On those top-of-the-line NVIDIA H100 GPUs, this technique leads to an up to 8-fold speed-up in what's called attention computations. That's one of the heaviest lifts for the AI brain.
But this is maybe the most incredible claim of all. You get all that memory savings, all that extra speed, and you lose nothing.
zero measurable loss in the AI's accuracy. And they proved it. They threw it at these super tough needle-in-a-haystack tests, where the AI has to find one specific little fact inside a mountain of text. And the compressed model? It was perfect. Scored identically to the original full-fat version.
Now, a discovery this huge doesn't just, stay in a lab and get published in a paper. No, this sent an immediate and pretty powerful shockwave straight through the global economy.
The market basically panicked. Investors got scared, fearing that demand for new memory chips was about to fall off a cliff. The thinking was, why buy more hardware when smarter software can do the job? And just like that, the stock prices of the biggest memory makers in the world, we're talking Micron, Samsung, SK Hynix, they just cratered, wiping out tens of billions of dollars in value in just a few days.
But here's a twist. A lot of analysts are pointing to this counterintuitive idea from way back in the 1800s. It's called the Jevons Paradox. And it basically says that when you make a resource, like AI memory, way more efficient and cheaper, you don't end up using less of it. Instead, it sparks an explosion of new ways to use it, which in the long run can actually make you need more of it than ever before.
And you know what? We're already seeing a real-world impact, not just in data centers, but on the shelves. In what was a pretty rare move for the industry, prices for high-end consumer RAM actually started to drop on Amazon right after this news came out, a direct ripple effect of a software idea. Look, what this really marks is a huge shift in how we think about solving AI's problems. For years, the answer has always been brute force. Just throw more silicon at it, buy more powerful hardware. TurboQuant is proof that a really clever algorithm can be just as potent as building a whole new chip factory. It's the start of a new era where software and hardware are designed together hand in glove.
And that really leaves us with one last big question. If a smart piece of software can suddenly make our hardware 6 times more efficient, what other unsolvable problems out there are just waiting? Not for a bigger chip, but for one more clever algorithm to come along and crack them wide open.